Hello everyone, and welcome to section 5.6 lecture. So in this section we're going to learn about the real zeros of a polynomial function. So remember, zeros of a function is the x values that you find when you set the function equal to 0. Right? So you have a function, in this case a polynomial function, and you set it equal to 0 and you solve for x. This gives you the zeros of the function. Right? So we're going, in this section we're looking for real zeros. Right? The real zeros are going to give you the x-intercepts of the functions. So real zeros are basically the x-intercepts. Okay, in the next section we're also going to talk about complex zeros. So you could have imaginary solutions, and those are significant also. It kind of fits in, so it ties together things for like a polynomial functions nicely in a neat bow. Alright, so we're going to learn a bunch of theorems that will help us figure out the real zeros. In a previous section we looked at finding zeros when the function factored. That's kind of a nice situation, but in this case, as we're going to consider functions that don't factor, so it's a little bit more challenging to find the zeros. So we're going to look at some theorems that will help us figure this out and also tie in with how a polynomial function behaves. So the first two theorems we're going to look at are the remainder theorem and the factor theorem. All right? So the remainder theorem says, suppose f is a polynomial function. If f of x is divided by x minus c, so this is a linear factor, so x minus a number, then the remainder is f at c. Right, so basically, if you divide the polynomial by the linear factor x minus c, the remainder of this division is equal to the function evaluated at f at c. All right? The factor theorem says, suppose that f is a polynomial function, then x minus c is a factor of f of x if and only if f of c equals 0. All right, so this quantity here is called a factor of the function if the function evaluated at this value c equals 0. So kind of tying in with the remainder theorem, then you say that x minus c is a factor of f if the remainder of the division is 0. Right? So kind of think of regular numbers. Right? If I divide 12 by 3, I get 4 with a remainder of 0. So you say that 3 is a factor of 12. Right? If you divide something, 13 divided by 3 with a remainder of 1, 3 is not a factor of 13. Okay, so that's what factor theorem says. Alright, so in this example here, we're going to use the remainder theorem to find the remainder when f of x is divided by x minus c. Then we're going to use the factor theorem to determine whether x minus c is a factor of f of x. So these go together, right? You're going to find the remainder, and then if that remainder is 0, you can decide, yes, x minus c is a factor of f. Alright, so here's my function, 4x to the 4 minus 15x squared minus 4, and the factor, or the binomial that we want to look at, is x minus 2. Alright, so if I do f of x to the 4 minus 15x squared minus 4 divided by x minus 2, right, the remainder of this is equal to the function evaluated at x equals to 2. So you plug in 2 into your function. So we get 4 times 2 to the 4 minus 15 times 2 squared minus 4. 4 times 16 we get 60. 4 minus 15 times 4 is 60 minus 4. 64 minus 64 equal to 0. Right? So we get a remainder of 0. And because it's a remainder of 0, then you say that x minus 2 is a factor of the function. Right. So why this is important to know is that now we can use that to factor this. Okay, so we can go through like a long division process to reduce this from a fourth power to a third power, and we can sort of find more factors, and basically the goal is to factor these functions. So like if I look at the origin function here, I don't know how to factor it. So we're trying to kind of develop a process of factoring these more complicated polynomials. All right, so this is kind of the first step. Let's look at B. All right, so part B. Again, we want to see if what the remainder is when we divide this function by this binomial. So the remainder is going to be f evaluated at -3. So we have 2 times -3 to the 6 minus 18 times -3 to the 4 plus -3 to the 2 minus 9. I'm going to use my calculator. So 2 times -3 to the 6 is 1458. Minus 18 times -3 to the 4, 1458, plus 9 minus 9. See, these cancels and this cancels, and I get a remainder of 0 again. All right? So again, we can say that x plus 3 is a factor of that function f of x. Alright, let's look at C. Same thing. We want to find the remainder of dividing this polynomial by this binomial. So we're going to plug in x is -1/3. So we have 3 times -1/3 to the 4 plus 3 times -1/3 to the 3 minus 3 times -1/3 plus 1. All right, let's simplify. So we have 3 positive 1/81 plus 3 -1/27 plus 1 plus 1. This is 1/27 minus 3/27 plus 2. -2/27 plus 54/27 gives me 52/27. All right, so this is the remainder. And this is not equal to 0. So we say that x plus 1/3 is not a factor of f of x. All right, there we go. So let's look at a couple more theorems. All right, so the first theorem here says number of real zeros. So it says a polynomial function cannot have more real zeros than its degree. So if it's 4th degree, the highest number of real zeros you can have is 4. You could have less, or you could have none. But this theorem gives the maximum number of real zero a polynomial function can have. The second theorem we're going to look at is Descartes' rule of sines. Right, so if we have f as a polynomial function, the number of positive real zeros of f either equals to the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less an even integer. And similarly, the number of negative real zeros of f either equals the number of variations in sign of the non-zero coefficients of f of negative x, or else equals that number less an even integer. All right? So let's look at what that means. So for these problems, first we're going to determine the maximum number of real zeros. Then use Descartes' rule of sign to determine how many positive and how many negative real zeros the function may have. So don't find the zeros, just figure out what the options are. Okay, so this kind of gives us some boundaries in trying to figure out how many zeros we're looking for. All right. So looking at the function in part A, we see that the degree is 4. Let's try that again. Degree equals 4. So that means that it has at most 4 real zeros. Right, so if we're trying to find the real zeros here, I know that I can have at most 4. All right. Now let's implement Descartes' rule of signs. So I know it's kind of very confusing just reading it. So let's do it in practice. Okay. So the first part, it's asking us to look at the number of variations in the sign of the non-zero coefficient of f of x. Okay. So that means you're counting how many sign changes there are for the coefficients. So going 5 is positive and 2 is positive. So it didn't change sign, it stayed positive. But from 2 to negative 6, there's a sign change because 2 is positive and negative 6 is negative. So there's one sign change here. Then I go from negative 6 to negative 5. There's no sign change because they're both negative. So here I have one sign change. Right? So this means that I could have, right, so it either equals the number of variations or else equals that number less an even integer. Okay? So this says that we can have one positive zero. All right? So there's one sign change. That means we can have one positive zero. Now, because it's 1, if I subtract an even integer from it, that's going to give me a negative number. So I don't have any other possibilities. So it's either how many sign changes, in this case 1, or that number less than an even integer. So I would have to subtract 2 or 4 or 6, but we can't go there because I can't have a negative number of zeros. All right, now let's look at the second part, which looks at the number of negative real zeros. So I need to figure out f at negative x. Okay, so I take my function and I plug negative x in here and simplify. So 5 times negative x to the 4, 2 times negative x squared, minus 6 times negative x minus 5. We get 5x to the 4, even power, the negative gets absorbed. Same here, 2x squared. This gives me plus 6x minus 5. All right, so again, I'm going to count how many sign changes. So we go positive to positive, no sign change. Positive to positive, no sign change. Positive to negative, there's one sign change. Okay, so here I'm looking at how many possible negative zeros I have. So this says I have 1 negative 0. Right? And again, because I can't subtract an even integer from here because I go in the negatives, this is the only possibility. Okay? So what I know now about this polynomial is that it has degree 4. It can have at most 4 real zeros. And this tells me that I can have one positive 0 and one negative 0. All right. Now the other two zeros, if they're there, they could be complex. Right? Because this gives me a maximum number of zeros of each kind that I have, positive or negative. All right, let's look at part B. So we're going to do the same thing. So figure out the maximum number, so count the sign changes in the original function in an f of negative x, and kind of get an idea of how many zeros we're looking for. All right, so you can see that we're sort of preparing to find the zeros, but we're not there yet. Okay, so this has degree 3. Okay, so that we have at most 3 real zeros. All right. Now we're going to look at how the sign changes. Okay, so negative to positive, it's one sign change. Positive to negative, another sign change. And negative to negative, no sign change. So these are 2 sign changes. All right, so this means I could have either 2 positive or 0 positive zeros. And these are real zeros. All right? So this is where that funny bit comes in. Either equals or equals that number less than an even integer. All right? So it's possible to have 2 positive ones, but it's also possible to have 2 less. Okay? So if I subtract the first even integer, I get 0. All right, let's look at f at negative x, and that will tell me the possibilities for negative zeros. So negative 2 negative x cubed plus 5 negative x squared minus negative x minus 7. Simplify. So because this is odd, the negative comes out. So positive 2x cubed. This is even exponent, so the negative gets absorbed. 5x squared plus x minus 7. Okay, so let's count how many sign changes. No sign change, no sign change, 1. So 1 sign change. Alright, so this means that I have 1 negative real zero. Okay? Good. So we're listing the possibility. We're kind of listing the possibilities of how many. All right, let's look at C. So this has degree 4. So at most 4 real zeros. All right. Then count the sign changes in the function. So no sign change, 1 sign change. Alright, so that means that I have 1 positive real zero. I'm going to take the function and plug in negative x. So I have negative x to the 4 plus 5 times negative x cubed minus 2. This is positive x to the 4 minus 5x cubed minus 2. I count the sign changes. So positive to negative is 1 sign change. No sign change here. 1 sign change. So we have 1 negative real zero. All right. Excellent. Okay. So let's progress. All right, so this will get us closer to finding the zeros. So the rational zeros theorem says that if the function is polynomial of degree 1 or higher, of this form, and this form is just what a polynomial looks like, right? Coefficients to variables to the integers. If p over q in lowest term is a rational zero of f, then p must be a factor of a0 and q must be a factor of an. Right? So basically, this theorem helps us list possible zeros, possible real zeros of our polynomial. And it's possible rational real zeros. So this helps us list possible rational real zeros of the polynomial. Alright, so it can it's still limited. Right? Rational means anything that can be written as a fraction. Right, so p over q. Alright, so this will miss out on any real zeros that are irrational, like stuff that has square root in it. So if there is a zero that's like square root of 2 minus 5, then this theorem will not find that real zero. But it will find anything that's rational. It's like 1 over 2, or 2 over 1, or 3 over 2, anything that can be written as a fraction, you can use this theorem to find those roots. Right? So in this example, we're going to use that theorem to list the potential rational zeros. We're not going to find them, we're just going to list them. Okay? So again, we're kind of moving forward. We're preparing to find the real zeros, but we kind of need to know those theorems to give us a method. Alright? Okay, so basically what we want to do, this is an, or a5, because we have coefficient of 5, and this right here is a0. Right? So we have a5 equals 1, and a0 equals 3. Right? So basically what the theorem says is that we're going to list all the factors of a5. Alright? So basically anything that divides into that number. So all the factors here are plus or minus 1. Right? And we're going to list all the factors of a0. Plus or minus 3. And you have to take the positive and the negative. Right? So basically the factors of a5 are called p. Actually this is p. And the factors of a0 are p, and the factors of a5 are q. Let me erase this. Right. P must be a factor of a0, q must be a factor of an. Okay, so p's are the factors of the constant term, and q are all the factors of the leading coefficient. Alright? So now the possible zeros are the p's over the q's. Okay, so here I only have a plus or minus 3, one possibility, and here I have plus or minus 1. Well, there's 2, but you can keep on combining. So the possible zeros are these factors over these factors. So plus or minus 3 over plus or minus 1, which is plus or minus 3. Alright, so basically these are possible rational zeros. And we can test to see if they're zeros either by plugging in to figure out if I get a remainder of 0, or by doing like division, synthetic or long division. Alright, let's do the next one. Okay, so we want to list the potential rational zeros. So we're going to say this is a3 right here equals -4. We want to list all the factors. Alright, so we have plus or minus 1, plus or minus 2, and plus or minus 4. So those are all the numbers that divide into negative 4. Alright, and then a0 equals the constant term, which is 6. And these factors, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Alright, so this is my P and this is my Q. Alright, the possible zeros are the P's over the Q's. So you basically take these and divide by these. So what I usually do, I go through all the P's divided by the first factor, and then all the P's divided by this one, all the P's divided by this one, in order to list everything. And sometimes you get repeats and you don't need to write them. Okay? So if I divide by 1, I get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And if I take each of these and divide by 2, 1 divided by 2 gives me plus or minus 1/2. 2 divided by 2 gives me plus or minus 1, which we already have. 3 divided by 2 gives me plus or minus 3 over 2. 6 divided by 2 gives me plus or minus 3, which I already have, right? Okay, so now we're going to take this and divide by 4. So I have 1 divided by 4 gives me plus or minus 1 over 4. 2 divided by 4 gives me 1/2, which I have. 3 divided by 4 gives me plus or minus 3 over 4. And 6 divided by 4 gives me 3 over 2, which I already have. Okay, so don't write down the repeats because you already have them there. So these are all my possible zeros. Alright, let's look at the next one. Alright, so A4, that's my leading coefficient is 6. The factors of this are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. A0 is 20, the constant term. The factors here are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5. Plus or minus, let's see, 4 times 10, and plus or minus 20. Alright, lots of them. Alright, so these are my P's and my Q's. Okay, so possible zeros are P's over Q's. Alright, so go through all of them divided by each of these in turn. Okay, so we basically list all of them to start with because we're dividing by 1. Plus or minus 1 and 2 and 4 and 5 and 10 and 20. Alright, then all of these divided by 2. Okay, so plus or minus 1/2. 2 divided by 2 is 1, it's already on the list. 4 divided by 2 is 2, which is on the list. 5 divided by 2 is not. 10 divided by 2 is 5, which we have. 20 divided by 2 is 10. Alright, now go all of these divided by 3. So plus or minus 1/3, plus or minus 2/3, oops. Plus or minus 4/3, and 5/3, and 10/3, and 20/3. Alright, let's see if there's any more. Yeah, there will be more. So divide by 6, we get plus or minus 1 over 6. 2 over 6 gives me 1/3. 4 over 6 gives me 2/3. 5 over 6 is new. 10 over 6 is 5 over 3. And 20 over 6 is 10 over 3. Alright, so all these are the possible real zeros. You can see in some cases there are many of them, which you have to try out, okay? And it just happens. Hopefully when you try them out, you can find them quickly because this can be a long process. Alright. Okay, so now we're going to put everything together and find all the real zeros of the polynomial function. Okay, and then use the zeros to factor f over the real numbers. So we're going to factor it, break it up into parentheses of either linear factors or irreducible quadratic factors. All right? So basically, we're going to look at the function. It says, oh, it has degree 3. Right? So it has at most 3 real zeros. Right? And then we're going to use Descartes' rule of sign to figure out whether they're positive or negative. So if you look at the function here, you can see there's one sign change. So this tells me I have one positive real zero. Okay? And then do f of negative x. So we get negative x cubed plus 8x squared minus 11x plus minus 20. And count the sign changes. So there's 1 and there's 2. So 2 sign changes. Which means I could have 2 or 0 negative zeros, real zeros. All right? So this kind of gives us a clue what to look for. All right? Now we're going to list all the possible zeros. Okay, so we're going to do the P's and Q's. All right, so let's look at A3 equals 1. So the factors of this are plus or minus 1. And A0 equals negative 20. So the factors here are plus or minus 1 and 2 and 4 and 5 and 10 and 20. All right? So this is my P and this is my Q. All right? So possible real zeros are P's over Q's, and because this is 1, it's just this list. So plus or minus 1, and 2, and 3, not 3, 4, 5, 10, and 20. Alright, cool. So now that I have this list, and I know there's 1 positive real zeros, or 2 or 0 negative real zeros, then I can test these. Okay, so you want to test these using what's called synthetic division. So we're going to take either the positive or negative and to test it out. Okay, so basically the way the synthetic division works, let's say I'm guessing the 0 to be positive 1. I'm going to put the 1 in the corner. You're going to list the coefficients of the function. So 1, 8, 11, and negative 20. Alright, and the 1 drops down. Then this multiplies by the number in the box. So 1 times 1 is 1. Then you add these. And then you multiply this by 1, you get 9. You add these, get 20. You multiply by 1, you get 20. And you add these and you get 0. Okay? So this is the remainder. If you get a remainder of 0, as we know from the factor theorem, if the remainder is 0 to the division, then that means that x equals 1 is, or you know that x minus 1 is a factor of that polynomial. Okay, So fortunately, we happen to have kind of fall on the first one we picked gave us a remainder of 0. Sometimes we have to do this lots of times, because if the remainder is not 0, you basically have to throw it away. You go, oh, it's not a 0, it's not a solution, move on to the next one. So potentially I had 1, 2, 3, 4, 5, 6, 12 different numbers to try out. But fortunately, this process is pretty quick in terms of the mechanics of it. So you can go through it fairly quickly. Alright, so we know that x minus 1, so the 1 comes from here, right? So x minus 1 is a factor of the function, and this gives me so why this is useful to use rather than just plugging in, because I could have plugged 1 into here and figure out the remainder of 0. But why this is useful is that this gives you the answer to the division. So if you put the x's back in here, this is 1x squared plus 9x plus 20 is the quotient, is the answer that you get if you divide the function by this factor. So that means that the function is equal to x minus 1 times x squared plus 9x plus 20. Right? So I get this linear factor times that quadratic. Right? Now you keep going. Now with a quadratic, you want to factor this if you can. Okay? And we can. This is x minus 1, x plus 4, and x plus 5. Right. So the first one, we had to list the possibilities and try out to see which one was the first 0. But once you get a quadratic, you can factor. That becomes easier. All right, so my zeros are x equals 1, x equals negative 4, and x equals negative 5. All right, so notice that I have 1 positive real zeros and 2 negative real zeros. Right? And this is the function in factored form. Right, so that's the answer. Find the zeros, which are here. Use the zeros to factor f over the real numbers. This is what we did here. All right, so that's what he was asking us for. All right, now you have this list of possible zeros here. I plugged in 1 and it worked. But notice that if you plugged in negative 4 and negative 5, that would have also have worked. So you could have gotten started that way too. If you started with negative 4 and negative 5, you would have gotten a different quadratic. But when you factor that one, you still end up with the same factors at the end. Okay, so there's a few ways to kind of figure it out, depending which number you pick first to try it out. All right, let's go to the next one. Should have left more room. Let me see if I can extend this. All right, I think I can have a little bit more room here. All right, let's look at this problem. Keep with blue. So I want to find the zeros of this polynomial function. So I notice it's degree 4, which means I have at most 4 real zeros. All right. Descartes' rule of sign will tell me possibly how many positive and how many negative. So let's count the sign changes. So 1, no, 2. 2 sign changes. So that means I either have 2 or 0 positive real zeros. All right, and let's do f at negative x. So when you plug in negative into the even power, it stays as it is, but when you plug them into the odd power, they change sign. It's going to be 2x to the 4 plus x cubed minus 5x squared minus 2x plus 2. You see, we want to be quick, right? Because there's lots of steps to the process. So no sign change, 1 sign change, 2 sign changes. So 2 or 0 negative real zeros. Okay. Now we're going to list them. Okay, so my q's are the factors of the leading coefficients. So plus or minus 1 and plus or minus 2. My p's are the factors of the constant. So plus or minus 1, plus or minus 2. So the possible zeros are the p's over the q's. So 1 over these and 2 over these. So I have plus or minus 1, plus or minus 2 when I divide by 1. And I have plus or minus 1/2 and plus or minus 1. Okay, so these are my possible zeros. Alright, now we got to try them out. So we have to do the synthetic division. Let's do over here. So pick one of these. Let's pick positive 1. So I'm going to put positive 1 in here. We're going to list our coefficients. 2, negative 1, negative 5, 2, and 2. Alright, so the 2 comes down, then multiplies the number in the corner. You get a 2. Add these. 1 times 1 is 1. Add these. Negative 4 times 1 is negative 4. Add these. Negative 2 times 1 is negative 2. 0. Alright, so we stumbled right away on one of them that works. So now, because you have 2 possible positive real 0 and 2 negative 1 or 0, potentially there's 4 of those that would work. Right? So it's not that unusual that it happens the first time because there's many that could work. Right? So the factor theorem says because this remainder equal to 0, then the x minus 1 is a factor of this. So that means the function I can write as x minus 1. And then here we fill things in with x's. So this is the constant. This has an x in front of it. This has an x squared. This has an x cubed. We have 2x cubed plus x squared minus 4x minus 2. Alright, so we factored it, but this is a cubic. I don't know how to factor it, so we have to do the rational root thing again. It has the same leading coefficient and the constant, so these are possible zeros to that. So we're going to do synthetic division again. Okay. Now 1 worked once, it could work again. Well, there's nothing that prevents it from working it again. But let's try another one. Let's say we're going to try 2. So we're going to list the coefficients of this. So not the original one, the cubic that's left over. So 2, 1, negative 4, negative 2. So we have 2. 2 times 2 is 4. We get 5. 5 times 2 is 10. We get 6. 6 times 2 is 12. And this gives me a remainder of 10. So 2 is not a factor, right? So that doesn't work. We're going to erase and try negative 2. All right, so negative 2 is on the list. So try that one. We have 2. 2 times negative 2 is negative 4. We get negative 3, positive 6, positive 2, negative 4, negative 6. Not a remainder of 0. That doesn't work either. All right. So 2 and negative 2 are not roots. All right. I'm trying to avoid trying the fractions. All right. So let's try negative 1. Come on, erase. Alright, let's try negative 1. 2, negative 2, negative 1, positive 1, negative 3, positive 3, 1. Negative 1 doesn't work either. Alright, let's try 1 next. Alright. I know we tried it before, but it's always possible that it works again. So 2 and 2, 3 and 3, -1 and -1, -3. No, that doesn't work. All right, so we've tried positive, -1, we've tried positive and -2. Now we need to try the fractions. Okay, so let's try 1/2. We have 2. 2 times 1/2 is 1. 1 plus 1 is 2. 2 times 1/2 is 1. -3. -3/2. That does not give me a remainder of 0. Okay, so that doesn't work out. Let's try -1/2. There you go. We have 2. 2 times -1/2 is -1. 0. 0 times -1/2 is 0. -4. -4 times -1/2 is 2. There it is! We got it! Nice. All right. So, good. Let's put it in. So, as I said, sometimes it comes right away. Sometimes you have to try lots of times. Okay. So now our function, we have that factor of x minus 1. Then this tells me that I have a factor of x minus -1/2, so plus 1/2. And then what's left over here is going to go into the last parentheses. So this is -4, 0x, and 2x squared. Okay, so this is 2x squared minus 4. All right, so let's try to factor this. So we're going to factor out a 2, x minus 1, x plus 1/2, x squared minus 2. And this one is like difference of squares. We have x minus 1, x plus 1/2. And this is not a perfect square, but we can say it's x minus square root of 2 and x plus square root of 2. Right? So even though those are not rational roots, we can still factor it using our methods. Right? So this is the factored form of the function. And we can see that the zeros are x equals 1, x equals -1/2, and x equals positive square root of 2, x equals negative square root of 2. Like this. There you go. And that's the process for finding zeros, rationals, sometimes irrationals of zeros of a polynomial. All right, let's look at the last one. Okay, so 3x cubed plus 6x squared minus 15x minus 30 has a degree of 3. So we're looking for at most 3 real zeros. We're going to look at sign changes. So positive, positive, positive to negative, one sign change. So we can have one positive real zero. All right. Let's plug in negative x. So this is going to be negative 3x cubed plus 6x squared plus 15x minus 30. All right. There's one sign change and 2. So we have 2 or 0 negative real zeros. Okay. Let's list them. So we got to list the factors of these. All right, so my q's are factors of 3, plus or minus 1 and plus or minus 3. My p's are factors of 30, so plus or minus 1 and 2 and 3, not 4, 5, 6, 10, 15, and 30. Lots of them. All right, so my possible zeros are the p's over the q's. So all these over 1 and all these over 3. So plus or minus 1, plus or minus 2, plus or minus 3, 5, 6, 10, 15, and 30. And then these over 3. So 1/3, 2/3. 3 over 3 is 1, which you already have. 5/3. 6/3 gives me 2, which we have. 10/3. 15/3 is 5, we have. And 30 over 3 is 10, which we have. Okay, so we have lots and lots of stuff to try. Alright, hopefully we get there soon. Alright, let's start with I'll start with 1. List the coefficients. So we have 3, 6, negative 15, negative 30. Alright. And like, you don't have to erase every time you do the division. I do because I left myself very little space. So let's see, 3, 3, 9, 9, negative 6, negative 6. That doesn't work. Alright, let's go to the next one. Negative 1. 3, negative 3, 3, negative 3, negative 18, positive 18. Doesn't work. Let's go to 2. 3, 6, 12, 24, 9, 18. No. Let's do negative 2. 3, negative 6, 0, 0. Negative 15, 30, 0. There it is. Yay! Alright, so remainder is 0. So that means the function has a factor of x minus negative 2, or x plus 2. So this original function can be written as x plus 2. And then this with the x's put in. So this is a constant, this has the x, this has the x squared. So 3x squared minus 15. Alright? This is a quadratic, so we're going to factor it. Let's pull out the 3 first. So x plus 2, x squared minus 5. And let's factor this as the difference of squares using square root of 5. So 3x plus 2, x minus square root of 5, x plus square root of 5. Right, so this is the factored form of my function. Alright, and the zeros are x equals negative 2, x equals square root of 5, and x equals negative square root of 5. Alright, so you can confirm, you can see that there's a 1 positive real 0, the square root of 5, and 2 negative real zeros, the negative 2 and the negative 5. Alright, let's look at next example. Solve each equation in the real number system. Basically, this is exactly like the other problems because we want to factor it and then find the zeros. Okay, so we're going to go through the same process. Alright, so we can see because this is 3, it's going to have at most 3 solutions. Let's look at sign changes. So here there are no sign changes, which means we have 0 positive zeros. Okay, this is very useful, right? Because I know not to look for positive solutions. Let's plug in negative x. We get negative 2x cubed plus 3x squared minus 2x plus 3. And count the sign changes. So I have 1, We have 2, we have 3. So we either have 3 or 1 negative zeros. Okay, remember it's either how many sign changes or you can subtract an even integer. So 3 minus 2 is 1. We can have 3 or 1 negative zeros. Alright, so let's list the factors of 2 and the factors of 3. So my q is plus or minus 1 plus or minus 2. And my p is plus or minus 1 plus or minus 3. So my p over q's, the possible zeros, these numbers over these numbers, so plus or minus 1 plus or minus 3, plus or minus 1/2, plus or minus 3/2. Right, so those are the possible zeros. Alright, now we're going to guess and do long division. So remember there's no positive zeros, so only try the negative numbers. So let's put a -1, list the coefficients, 2, 3, 2, 3. We have 2, -2, 1, -1, 1, -1, 2. Alright, so that doesn't work. Alright, erase and try again. So we're going to try -2. Oh, not -2, -3. -2 is not on the list. Alright, so 2, -6, -3, 9, 11, -33. Yeah, that doesn't work. Remainder is not 0. Okay, must be fractions. Alright, let's see. We should try -1/2. Alright, so 2 times -1/2 is -1. 2 times -1/2 is -1. 1 times -1/2. That doesn't work. Alright, let's try -1/3. There we get 2, -2/3. Let's see, 3 is 9/3, minus 2/3 is 7/3. Oh, this looks bad. Oh, that's not, sorry. 1/3 is not on the list. I'm glad, because that was not working out. What's on the list is -3/2. Alright, so 2 times -3/2 is -3. Then we get 0, and this is 0. This is 2. This is -3. This is 0. Yay, we got there! Alright, so this is going to factor as x plus 3/2. And then from here, we get what goes in the second parentheses. So this has an x, this has an x squared. We have 2x squared plus 2 equal to 0. Alright, this factors with a 2. 2x plus 3/2 x squared plus 1. But this does not factor because it's a sum of squares. So this does not give you real 0, it gives you imaginary zeros. So we get x equals -3/2. It says solve the equation in the real number system, so the only real answer is -3/2. This is going to give you x equals plus or minus I, which are solutions, but they're complex. Alright. So we're interested in these in the next section. And we're going to basically do this in the next section too, so it's useful knowing how to do it. Alright, let's look at B. So same deal. We have at most 3 solutions, 3 real zeros. Let's look at sign changes. So one sign change, 2. So we have 2 or 0 positive zeros. Let's do f at -x. So -2x cubed minus 11x squared minus 10x plus 8. Let's see how many sign changes there are. negative, negative, positive. So 1, negative, 0. Alright, let's see. This is Q factors are plus or minus 1 and plus or minus 2. P factors are factors of 8, so plus or minus 1, 2, 4, and 8. So P over Q is going to give me all of these 1, 2, 4, and 8. And these divided by 2. So we have 1/2, 1 which we already have, 2 we already have, 4 we already have. Okay, so these are my possibilities. Alright, let's divide. Alright, so we're looking for 2 positive, 1 negative. Let's try some positives. I'm gonna start with, I don't know, let's start with 1/2. Like the fractions have been good recently. Negative 2, 11, 10, and 8. Watch them not work this time around. So we have 2. 2 times 1/2 is 1. Negative 10. Negative 5. 5. Oh, doesn't work. All right. Let's try negative 1/2. Might as well. 2, negative 1, negative 12. 6, 16. Negative 8. Yes! Remainder of 0. Perfect. Good. So that works. So I can factor as x plus 1/2. And then put x's in. 2x squared minus 12x plus 16 equal to 0. Let's factor this. So 2x plus 1/2. X squared minus 6x plus 8. And keep factoring. 2x plus 1/2, x minus 4x minus 2. You can see another of the 2 numbers on the list. So if we tried these, we would have made progress. Alright, so the solution will be x equals negative 1/2, x equals 4, x equals 2. Alright, so those are the zeros. Alright, let's do this one. Okay, so this one is x to the 4, which means we have 4 possible zeros. Let's count sign changes. 1 sign change. Okay, so we have 1 positive real 0. Let's plug in negative 1, negative x. So all the ones with even powers stay the same, but the ones with odd powers change sign. So 2x4 minus x3 minus 24x squared minus 20x plus 16. And let's count the sign changes. 1, 2. So we have either 2 or 0 positive, negative zeros. Let's see. Oh, 2 sign changes. 2 or 0. Yeah, there's 2 sign changes here. So 2 or 0, positive zeros, or 2 or zeros, negative zeros. Alright, so my P, my Q, this is 2, so plus or minus 1 and plus or minus 2. And my P factors of 16, so we have a bunch, 1, 2, 4, 8, and 16. Alright, so P's over Q's, we have 1, 2, 4, 8, and 16. And then D's over 2, so plus or minus 1/2, and that's it, because this is 1, 2, 4, and 8. Good. Alright, let's start doing some division. So let's try out 1. So 2, 1, negative 24, 20, and 16. So 2, 2, 3, 3, negative 21, negative 21, 1, and 1. That doesn't work. negative 1. 2, negative 2. Negative 1, 1. Negative 23, 23. That's too big. Alright, so that doesn't work. Alright, let's try 2. 2, 4, 5, 10, negative 14, negative 28, negative 8, negative 16, 0. Yay! We got there. So the first factor is x minus 2, and then we have 2x cubed plus 5x squared minus 14x minus 8. Alright, so here we're left with the cubic, so we need to do synthetic division again. So we can use some of the same factors, right, because we have 2 as the leading coefficient and 8 as the constant. So the 16 is not going to work, but all the others are, okay? Now we already tried 1 and negative 1, so that's not going to work in here either, right? So let's keep trying. Like 2 could work again, but let's try negative 2. So 2, 5, negative 14, negative 8. Right, so I have 2, negative 4, 1, negative 2, negative 16, 32. Alright, that doesn't work. Let's try 2 again, actually. I have a feeling about 2. 2, 4, 9, 18, 4, 8. Yeah, it worked again. Alright, so that means we have x minus 2, and this breaks down as x minus 2, and then 2x squared plus 9x plus 4 equals 0. Alright, this is a quadratic, and I think it factors. So let's say we have x minus 2 squared, 2x plus 1, and x plus 4. Right? So that works. Good. So the zeros are x equals 2 twice, it has a multiplicity of 2. Then x equals negative 1/2, and x equals negative 4. So those are my solutions. All right. Okay, let's look at the intermediate value theorem. So the intermediate value theorem, this is kind of like, alright, so you tried all that and you couldn't find any solutions, probably because you don't have any rational zeros. Okay, but it's still possible to have real zeros that are irrationals, like square roots. Right? But the rational root theorem doesn't work in finding square root solutions. So you're kind of stuck to trying to approximate solutions. So the intermediate value theorem comes in to try to kind of guess where you could have a real solutions. All right. So what you do is you look at intervals, and you want to see if the function changes sign from one end of the interval to another. Okay, so the idea is if I have a function over this interval, so x is negative 3 and x equals negative 2, and if I have the function be change sign with this within this interval, then it has to cross somewhere in there and give me a 0. Okay, now you don't know where it's going to cross, but at least you know where to start guessing. All right. So what we do is we plug in both ends. So I'm going to plug in negative 3, we're going to plug in negative 2 and figure out what the function is. We have 3 times negative 3 cubed minus 10 times negative 3 plus 9. Alright, let's erase this. So 3 times negative 27 is negative 81 plus 30 plus 9. Negative 51 plus 9 gives me negative 42. Alright, so f at negative 3 is negative 42. So it's down here somewhere. Okay? Alright, now let's do f at negative 2. So 3 times negative 2 cubed minus 10 times negative 2 plus 9. We get 3 times negative 8 is negative 24 plus 20 plus 9. This gives me positive 5. Alright, so the function is positive 5 at this end. Okay, so this is a polynomial function, which means it's not going to have any breaks in it, no asymptotes, no things like that. So if it starts down here and it ends up here in that interval, that means it's going to do something like this, and it has to cross through the axes. So it has to have a 0 somewhere between negative 3 and negative 2. Alright, so we showed that that's the case. So if you show a sign change, there's a sign change. Therefore, the intermediate value theorem tells you there must be a 0 in the interval negative 3 to negative 2. Alright, so that's what the intermediate value theorem is. Alright, let's look at example 7. Alright, so the next few examples we're going to graph the polynomial function. So graphing is, we're going to look at end behavior. We're going to find the zeros so we can figure out the intercepts and their multiplicities. And we're going to find the y-intercept. Alright, so with what we know now, we do all that stuff. Okay? So let's see, the end behavior is you're looking at the leading term and the leading coefficient. So this is x cubed. Alright, so that means it's positive coefficient with odd power, so it goes up and then down. Okay, so at positive infinity is going to positive infinity, and negative infinity goes to negative infinity. So you know that it's going to look somehow like that. Alright, let's find the y-intercept because that's easy. So we set x equals 0, we get y equals negative 20. Alright, let's do these by tens. So 10, 20, 30, 40, and 50. 10, 20, 30, 40. Alright, so my y-intercept is right here. Alright, now we need to figure out the zeros and the multiplicity. So this is where most of the work comes in, because we need to go through all the stuff that we just learned. Alright, so it's cubic, so it has to have at most 3 real zeros. Real zeros means intercepts. Alright, let's look at sign changes. So there's one sign change. So we have one positive 0, real 0. And let's look at f at negative x, which is negative x cubed plus 8x squared minus 11x minus 20. Let's count the sign changes. 1, 2. So we have 2 or 0 negative real zeros. Alright, so that's what we know. Let's list our p's and q's. So q's are plus or minus 1. P's are all the factors of 20. So 1 and 2 and 4 and 5 and 10 and 20. Alright, so p's over q's are just these ones because we're just dividing by 1. Alright, let's try them out. So let's try 1. Coefficients are 1, 8, 11, and negative 20. We have 1, 8, 1, 9, 9, 20, 20, 0. Good, we got it for a shot. So factor is x minus 1. parentheses, we have x squared plus 9x plus 20. We factor this more. We have x plus 4 times x plus 5. Alright, so this is my function in factored form. So the zeros are x is 1, x is negative 4, and x equals negative 5. Right? If you remember, the multiplicities are the exponents. So all these have multiplicities of 1. Okay, so let's graph these intercepts. So with odd multiplicities, it's going to cross through. So x is 1, x is negative 4, and x is negative 5. Alright, those are really, really close together. Alright, so let's see if we can make a good job here. Pick a nice color. Alright, so it has to start down here, because that's what the end behavior says. Then it passes through negative 4, then it passes through negative 5, then it's going to pass through negative 20, then it passes through 1, and it goes to infinity. Alright, so it's probably just a little bump here, like this. There we go. Okay, so that's a sketch of that polynomial function there. Alright, let's look at another one. We want to graph this. So end behavior. So look, in the leading term is x to the 4. It's positive and even, so that means it goes up at both ends. Okay, so it's going to do something like this. Y-intercept. Plug in x is 0, and we get y equals negative 2. Alright, so here's negative 2. Alright, zeros. So we have at most 4 zeros. We're going to look at sign changes. So we see there's one sign change in the original function. So 1, positive, real 0. Alright, let's do the f at negative x, which is x4 plus x squared minus 2. Nothing changed. There's a sign change. So 1, negative, real 0. Alright, good. So there's like 2 zeros unaccounted for, which are probably complex. Q's are plus or minus 1. P's are plus or minus 1 and plus or minus 2. So P over Q's are plus or minus 1 and plus or minus 2. Good, not that many to choose from. Okay, so let's try 1. So coefficients. Now notice there's some powers missing. Alright, so we need to write this as x4 plus 0x cubed plus x2 plus 0x minus 2. This is important when you do the synthetic division. We have 1, 0, 1, 0, negative 2. So 1 times 1 is 1. 1 times 1 is 1. 2 times 1 is 2. 2 times 1 is 2, 0. Alright, so it factors as x minus 1, and then x cubed plus, I have too many. 1, 0, 1, 0, negative 2. x4, x cubed, x squared, x constant. X cubed, x squared, x squared plus 2x plus 2. Alright, good. Alright, here we could do synthetic division again. Let's try negative 1 on this. 1, 1, 2, 2. So we get 1, negative 1, 0. 0, 2, negative 2, 0. Good. So this factor is x minus 1, x plus 1. And we have x squared plus 2 left over. Alright, so if we want to find the zeros, this is quadratic. It doesn't factor anymore because it's sum of squares. So we get x equals 1 and x equals negative 1 are my real zeros. They both have a multiplicity of 1. Alright, so let's put everything together now. Okay, so we have a 0 at negative 1, a 0 at positive 1, and my function goes up at both ends. Alright, so let's draw it this way, and then it goes here, and it goes like this. Okay, now I'm not sure if there's any extra wiggles or anything. I mean, it could go like this because it's x to the 4. It probably does. Alright, if I just graph that, it's like a parabola. So I think an x to the 4 kind of does something like this, like a W. Like that. Okay? Alright. Okay, let's do this last problem. Okay, so let's look at end behavior. So 4x to the 5 is my leading term and coefficient. It's positive, it's odd, so it goes up at one end, down at the other, like that. Y-intercept, plug in 0. For x, we get 0, 2. Okay, so we get down here, it's going to pass through x, y is 2, and then it goes up there. Alright, let's look at zeros. So 5 at most. Wow, that's a lot of them. Alright, let's see how many sign changes. So 1, 2. So either 2 or 0 positive roots. Positive zeros. Alright, let's look at f at negative x. So negative 4x to the 5 minus 8x to the 4 plus x plus 2. We have one sign change, so 1, negative 0. Okay, let's list them. Fortunately, there aren't too many. So PQ comes from the 4, so plus or minus 1, plus or minus 2, plus or minus 4. And P is plus or minus 1 or plus or minus 2. So P over Q is 1 and 2. Then we're going to do over 2. So we get 1/2 and 1. And then over 4 we get 1/4 or 1/2, which we already have. Alright, so those are my possibilities here. Alright, so let's do the division over here, the little corner. Let's guess. Let's see, would 1 work? I don't think 1 works. Let's try 2. Alright, let's see. I think we're missing a couple of powers. So we have 4x to the 5 minus 8x to the 4 plus 0x cubed plus 0x squared minus x plus 2. Okay, so you gotta put the 0 coefficients, otherwise things get messed up. We have 4, negative 8. Okay, let me do over here because I'm gonna try to save this and post it. Alright, so let's do negative 2. Positive 2. 4, negative 8, 0, 0, negative 1, and 2. So we have 4, 8, 0, 0 times 2 is 0, 0, 0 times 2 is 0, 0, times 2 is 0, negative 1, negative 1 times 2 is negative 2, 0. Okay, yay, we got something. Alright, so let's see how it factors. So this is going to be x minus 2, 4x to the 4 minus 1. All right, good. Now we can factor this without having to do long division. So this is x minus 2. This is 2x squared minus 1 and 2x squared plus 1. All right, so we have x minus 2. This factors as square root of 2x minus 1 and square root of 2x plus 1, and this one does not factor. All right, so my zeros are x equals 2, x equals 1 over square root of 2, and x equals negative 1 over square root of 2. So we have 2 positive zeros and 1 negative 0 and 2 complex zeros, basically. All right, let's plot those x-intercepts. Let's do nice purple. So x equals to 2, that's one of them. 1 over square root of 2 is like 0.7, I think. All right, so we have 1 over here, and then negative 1 over square root of 2 over here. All right, so let's see if we can draw something sensible. All right, they all have multiplicities of 1. Okay, so this is a multiplicity of 1, and this one, and this one. So they're going to cross through. Okay, so we start here. It's going to cross through. Go to the y-intercept. Then go down, cross, go up, cross, and then back up. Something like this. That's the graph. All right, there we go. So this is the end of this section.